Welcome to 90 Notes. Let's have some fun with numbers. Now, I made these three columns for you. Well, imagine it's just one long continuous column, just wrapping around like that. And I started with a 1, we added 3, we got 4. Recognize this series? You will. We add the next odd number, which is 5. After 3 is 5, the next odd number, of course. And 4 and 5 make 9. We're going to add the next odd number, which is, of course, 7. 9 and 7 makes 16. So we see where this is going. We're going to add the next odd number. How about 16 and 9? 16 and 9 is going to make 25. And then we'll go 25. We'll add the next odd number, which is 11. And we're going to add the 25 to the 11, 36. 36. The next odd number is 13. So we're going to add that 13 center over there a little better. And we're going to get 49. And of course, the next odd number, and we could do this all day, and we will, is going to be 64. And let's see, we add 17. 64 and 17, add that up really quick, 81. What's the next odd number? Well, that's going to be 19. And we're going to add 81 and 19, and we hit the triple digit mark, 100. Okay, now, I just made this to continue. So take this 100 and shift it up here, right there. Boom. See, we're just repeating it. Okay. After 19, what comes next? Well, that'll be the next odd number is 21. Add them up, you're into 121. Let's add 23, the next odd number, and we're at 144. All right, how many of you done this before? Come on, raise your hands. We have the next odd number, 25. Well, let me see, that's 169. We can see that. Oh, now we got to think a little bit. We're going to add 27, the next odd number. Okay, carry the 1, and you've got 196. 196, let's add 29. Oh, we're crossing the 200 mark, 225. And we're going to add 31 this time. 50, oh, that's easy. We could do that. 256. Add 33. It's going to end in a 9, and it looks like an 89. 289. Let's add 35. We add 35 to 289, and you're going to get 324. Okay. Next odd number, 37. All right, 50, looks like a 61, and it is 361. Okay, we're down the bottom of the second column, and we're going to go up to here and just repeat that 361. So just continue it from there. 37. We're going to add the next odd number, 39. Ooh, and then a 0 for once. Look at that. That's looking like 400. Next odd number, 41. Well, that's an easy addition. 441. Let's add 43. Still not that bad. What is that, 84? Yeah, you can do that in your head. We're going to add 45. Oh boy, now we're going to cross over to the 500s. 529. And then we're going to add ruh-roh. I said, oh, that's terrible. That should be 40. What should that be? 47. Let's add 47. I must have messed that one up. Sorry about that, everybody. And even got the color wrong. And that's going to be 576. Okay, well, we can bounce back from this. Oh, doggone it. I hit the wrong thing. Maybe it's up there. Oh, I guess I didn't do this. 49. So we're going to add 49. How embarrassing. And let me see, we add that, and what do we get? We get 625. Now, I'm going to stop there because that's where your paper stops. Yeah, it does. I know because I made it. I think it stops there, and if it doesn't, you can stop there anyway, because that's as much as I'd expect you, well, to be familiar with. These numbers, these numbers are not random. Oh, no, no. We made this little series, this little pattern, our little magic math. But most of you, you're grinning because you recognize these numbers. These are all special numbers. And this is the set of square numbers. Now, go ahead, take a good look. Oh, yeah, 15 squared, 225, 256. They're all coming back to you. Now, the fact is, in this chapter, you're going to end up memorizing the first 25 squares. Not because I'm going to make you, just because of habit. It'll just become familiar to you. And there they are. So you can kind of keep this, keep this scrap paper. And you could see, you could just jump down, for example, into the 28th item here, and we could pull up our calculator. And let's just say we said 28, and we squared it 784. So I could even jump all the way down here, and I know 784. Pretty slick, huh? Okay. Oh, sorry about that mail. It just must be a popular guy on this, this last quarter of the semester. Hey, but you probably thought this chapter is about right triangles. Well, you come to the right place. Okay, wait. Before we move on to that stuff, let's back it up a little bit. Let's go way back to elementary school. Remember this? Oh, yeah, the factor tree. Now, when I say factor, 72, what can we divide that by? Well, we can divide it by a lot of numbers. Could we divide it by 7? Well, sure, but you won't get a whole number response. You won't get a whole number quotient. So we're talking about on the set of whole numbers. We remember our divisibility rule. 7 plus 2 is 9, so it's divisible by 3, it's divisible by 9. It's divisible by 2 because it's even. As a matter of fact, those of you that know your times table, you are always taught 8 times 9. And that's 72. And that's a fact. Now, you then could say, well, wait a minute. I could split them this way. And I can say, hey, 8 is 2 times 4. 9 is 3 times 3. And I can further look at that 4 and say, isn't that just 2 times 2? And yes, it is. Move that out of the way. This was the factor tree that you learned way, way, way back in elementary school. But it's coming back for a purpose. Now, you could have also taken this, and you could have also just done this. You could have said, I prefer to think of 72 as 2 times 36, which it is. And then you could say, okay, and 36 is 2 times 18, it's even. 18 is even, it's 2 times 9. And of course, 9 is 3 times 3. Well, I mention this because this speaks to something called prime factorization. This is an important concept in arithmetic. We know that no matter how we express 72 as a product of primes, it is 2 times 2 times 2 times 3 times 3. Or 2 used as a factor 3 times, 3 used as a factor twice. That's so important that it has a name. That is called the fundamental theorem of arithmetic. So why are we talking about it in geometry? This is why. It's time for radicals. A little bit of radical review. You're going to do some radical practice in this. And you're going to need that when we're exercising our Pythagorean theorem. So our 72, see our factor tree there, again, the product of primes. Watch this. Let's review this little exercise. We could separate it this way, 8 times 9. Well, we know that the product of radicals well, they can be expressed here as, well, product of radicals, which are, oh, how do I say this? Factors of the radicand. Oh, that was, yeah, I could do better. Somebody could do better. Square root of 9 is 3, the whole number 3. Radical 8 is still a radical. But then you say, wait a minute. I can factor that out. The square root of 4 times the square root of 2. The square root of 4 is, of course, the whole number 2. 3 times 2 is 6. And I'm left with this number. The square root of 72 can be expressed in simplified radical form as 6 radical 2, the whole number 6, times that irrational number, which is the square root of 2. Now, there's a fun way to look at, well, I guess could show you in class. Look at all these. All right, I'll show you right now. If you have the prime factorization like this, and let's say you're taking the square root of 72. Every time you see a pair of them, cross them off. All right, that's 3. That's 2. 3 times 2 is 6. What's left? Radical 2. That works 100% of the time. I'm not saying it's a great method or anything, but it does work. Watch this. Yeah, I'm going to show you this is what works better, is instead of going through this tedious 5 steps, is that you look at this and say, well, I recognize a larger perfect square. The largest perfect square that is a whole number factor of 72 is 36. Now, this cuts through all the mustard there because the square root of 36 is 6, and you are done. Much faster, isn't it? Okay. Well, if you like that, I guess you're going to like what we do next. This is the next part of your worksheet. You are going to, without your calculator, you're going to simplify the following radicals. Ready? Let's go. Okay, I had to scale the font down so I could fit it. I gave you 12 of these little samples here. Hey, first one we already know that because we spent an exhaustive amount of time on that. All right. Now, number 2, well, you'll learn later on that it's actually a cubic number, but for us, we're going to say, what is it? It's 3 times 3 times 3, or it's 9 times 3. The square root of 9. I'm going to factor it that way. The square root of 9 is the whole number 3. I've got 3 radical 3. Again, that's the number 3 times the irrational number radical 3, which is about 1.7 something. Let's see what it looks like as a decimal, just so we experience this. 3 radical 3 is, again, 3 times, and the square root of 3, which equals about that. But there's times when it's to our advantage. So again, you should know that it's a number bigger than 5, but there's times when it's to our advantage to express it as a product of a whole number and a radical. Now, you're thinking back to these numbers, flipping over here, what's the biggest? Look at that. What is the biggest of those perfect squares that you can imagine are in there? Jumps out at you. It's, of course, 100. Square root of 100, 10. 10 radical 2. So about 140, about 14.1. Messed up there. Okay, number 4 is already indicating a product of a whole number and a radical. But that radical can get simpler. You look at that 32 and you say, well, I know it's divisible by, let me see, 4, it's divisible by 8. Well, if you really look carefully, you'll say, 16. That's the biggest perfect square. So look what you've got. You've got 5 that whole number 5 is still there, times the square root of 16 times the square root of 2. So it is 5 times the whole number 4 times radical 2. And we can multiply the 5 and the 4. We have 20 times radical 2. Whew, you guys getting this? Yeah, of course. It's good review for our getting us ready for this chapter. So everybody, what's 4 plus 9? Well, you know, it's 13, but please, oh, excuse my dear Aunt Sally. Yes, this is the radicand symbol, or this is the radicand, the expression that's under the radical symbol. When that bar extends over like this, that's the same as parentheses. So please excuse my dear Aunt Sally. It is simply going to be radical 13, and you're done. Now, if you were thinking this, that looks pretty, it's just that it's wrong. So yuck, let's make that line a little bit redder and a little bit darker. Bad math. So, can't do that. In the same way, I'm looking at this one. Now look, I've got squares. I'm squaring numbers, and then I'm taking the square root, and you're saying, well, wait a minute. If I take a square and I take a square root, am I doing that? And 3 plus 4 is 7? Is that what I'm doing? Well, of course not, because that would be just as wrong. Because, again, that division bar, or division bar, sorry, the radical symbols here inside this radicand, that is a grouping symbol. So the correct way would be to say, simplify the squares, or square your two bases, add them together, and now it just jumps out at you. Easy as 3, 4, 5. And we'll see something magic about that tomorrow. All right, so number 7, now it stole our thunder. We got this. 5 squared, 25. 12 squared, 144. So what do you got? Boom, shakalaka. Add those two numbers together, 169. Square root of 169, you'll always, hey, wait a minute. We could just flip back over here. Look at that. Where do we have 169? Yes, we do. That's 13 squared. Look at that. All right, so I guess the answer is 13. Oh, all right. We're getting down there. We're halfway through these. Now, this is a little funny. Okay, I'll just say it this way. It's just bad form. We don't keep the radicals in the denominator. So we are going to rationalize the denominator. That sounds pretty cool, doesn't it? Now, you learned a long time ago that you can multiply anything times 1, and it is itself. Well, this is true here too. So go ahead, we're going to multiply it by 1. That's what we mean. Well, radical, any non-zero number divided by itself is also 1. See, I'm really just justifying it. You see, I'm going to rationalize the denominator. Because now, when I multiply radical 5 times radical 5, I get the whole number 5. Does that make sense? Well, of course, you could think of it multiple ways. Radical 5 times radical 5 is radical 25, which is, of course, 5. Or the square root and the square. These two operations are going to undo each other. Square root of giraffe times the square root of giraffe is giraffe. It's that simple. So here we go. The denominator becomes 5. Now the 5 is a rational number, and the numerator is radical 5. Now, personally, I don't really care a whole lot about this, but your Algebra 2 teacher is going to be a stickler on this. We just do the fun stuff in geometry. Yeah. What did we do? Oh, yeah, we're down here already. So let's do it again, rationalizing the denominator. This one will come out a little bit different. So again, the denominator is radical 3. multiplied by radical 3 over radical 3. You got this. Boom. And now you're thinking, radical 3 times radical 3, that's going to be the whole number 3. And you're thinking, look how clever I am. But then you say, aha, even better. I can divide out that factor of 3 like that. So what am I left with? 2 radical 3. Now, let's do a couple additions, and then we'll call it good. And this will be, then you can turn in this one assignment. Right, I've got 7 radical 2 plus 3 plus, I'm sorry, radical 3 plus 6 radical 3 and plus a radical 2. Even color-coded so they jump out at you. It's like I'm adding giraffes and elephants. I got 2 different animals here. Well, maybe if you like the abstract better. What if I had 7x plus y plus 6y plus another x? You can combine the like terms. Oh yeah, remember that? 7x plus x, that would be 8x. 1 giraffe plus 6 giraffes, 7 giraffes. So how do we do it? We combine the like terms. Oops, what did I say? I think I messed up there. All right, but again, there's 7 radical 2's plus another radical 2, 8 radical 2's, 1 radical 3 plus 6 radical 3's, 7 radical 3's. Think of it that way. All right. Now, we're getting there. On the surface, you look at these two and say, they are dissimilar, or they are not like terms. And you would just say, well, then I guess they just stay at 2 terms. But you would have missed something. You got to put them in their simplest form first. So I classify this as a trick question that your Algebra 2 teacher will hit you with. You're looking at that saying, wait a minute, not in its simplest form. 12 is 4 times 3. I've got a perfect square there. 27 is 9 times 3. That also contains a perfect square. Let's factor out those perfect squares. And you say, wait a minute. Now you're saying, look what's happening. Now they're the same animal. I've got 2 radical 3's and 3 radical 3's. 5 giraffes. Beautiful. All right, so now you kind of figured out how this works. You're going to do the same thing here. 72, we already know from problem 1, that's going to be 6 radical 2. 75, well, let me see, that contains 25. That's the biggest perfect square there. So that's going to be 25 and times 3, and 48, I think that's 16 times 3. So go ahead and work it out. So again, 6 radical 2, 75 is 25 times 3, so it's 5 radical 3, and 48 is 16. Again, 16 radical 3. Now, the radical 2 and the radical 3 are dissimilar terms, but I've got radical 3 as a term twice, so I can perform the subtraction, and then I would have that 6 radical 2 plus 1 radical 3, or as we write it, radical 3. Whew. Well, I hope you had a good time and had fun reviewing your radicals, and get this all turned in. And if you're not my student, well, thanks for watching. And, well, for anybody, thank you for watching Nani.